Okay, let's start. This is 20, 29, huh? Okay, something. Okay, so we have been looking at noise. So let me summarize some of the takeaways from last class discussion. So we saw that if we have a linear two-port network, the noise generated in this network in, let us say, the output open circuit voltage or in the output short circuit current. To model this noise, we use the notion of input referred noise. So the idea is the following: we say that the network is noiseless and we try to model the noise using something at the input, and we saw that essentially we need both a voltage and a current source to properly model the noise generated in the network for any value of the source resistance Rs. So this guy is the input referred noise voltage. I'll call it Vn in. This is the noise current In in. And we also saw how we can go about computing this voltage and current. So firstly, to find the voltage, we try to wire up as this case. Okay, let me just write it. This is noisy, this is noiseless. To find the voltage, we try to make up a scenario where the noise is coming only due to the voltage, and that will happen when Rs is basically 0. That boils down to shorting the input. So you short the input in the noisy network, find, let us say, the path spectral density in the current, and then you do the same thing. And then you do the same thing in the, what the hell, okay. You do the same thing here. So here you find the transfer function from this voltage to the output, divide the transfer function squared, you get the input referred noise PSD. Similarly, to find the current, you wire up a case where the noise is coming only due to the current, and that happens when Rs is infinity. So once again, in the noisy network, you find the path spectral density in your current or voltage, and then you find the transfer function from this guy to this guy, divide the path spectral density by magnitude squared of the transfer function, that gives the current path spectral density. And so here we can observe that if the input resistance of the two-port network is infinity, to model the noise generated, you only need the voltage source. So that is one nice thing to take away. So if the input impedance is infinity, then only Vnn is enough to model. And if you still try to find out this current, it will come out to be 0. Right? So this is nice because if you think about it, in all the possible candidates we have for making an op-amp, the input is given to gate. So if you ignore the gate capacitance, the input resistance is infinity. So to model the noise in all our op-amps, strictly speaking, we only need voltage. I'll just write noise in op-amp. This is assuming the gate capacitances are ignored, right? So, and as an extension, we also saw in the last class that ideally, if you take a MOSFET like this, the noise generated in the MOSFET is to be modeled as a parallel current source connected across drain and source, because the noise is in the drain current mainly. But once again, if you ignore the gate capacitance for this guy, the input resistance is infinity. So which means to model this noise, you can also, to model the noise here, you just need a voltage at the input. So you can model the noise of this guy using an input referred noise voltage. So the current has a path spectral density of 4 kT gamma times Gm. The voltage here will have a path spectral density of 4 kT gamma by Gm. So this is again assuming that the gate capacitance is 0. So essentially at low frequencies, this is perfect. Cool. So the other takeaway is this. If you recollect, we calculated the noise in a cascode also. This is a small signal for a cascode, and here if I look at the noise contributed by the cascode transistor, right? So let's say you find the short circuit current here. If the output resistance of this main current source is infinity, then in small signal this is basically open. So what is the portion of this current that flows to the output? 0. Essentially the cascode transistor contributes to 0 noise, provided the bottom guy has infinite output resistance. If not, it will get attenuated by a factor. We found out it's 1 plus, so of the order of 1 by GMR0. So that's why cascode is a nice thing. This guy silently comes without making any noise and helps to boost your gain. Okay. Cool. So now we have looked at a lot of single stage structures. So what next? Yeah, let's directly go and attack our 5 transistor OTA. So let me first draw the schematic quickly. So this is this guy. So make the direct connection here. Let me also label this M0, M1, M2, 3, M4. Cool. So again, the first of all, you can see that again the input is applied to the gates here. So the input impedance is infinity, ignoring gate cap. So you only need to find the noise voltage. So to find the noise voltage, what do I do to the input side? You have to short it. So one difference is, see here we have 2 inputs, right? So to model the noise, you can model it as a voltage source either at the non-inverting side or at the inverting side, or you can say half there, half here, doesn't matter. Somewhere at the input we can model this. So, and once again to find the contribution due to this voltage noise, we have to short the input. So first let me short that here. And let us say you find the short circuit noise current, right? So you find the short circuit noise current and then divide it by the transfer function square. So let's first find the transfer function. So in the noise model, let us say I am adding an equivalent voltage noise here. Okay. So what is the transfer function from this differential input to the output? I mean, if this is I out, and if I call this as say V1 and V2, what is I out by V1 minus V2? It is a short circuit transconductance, which is basically GM of the diff pair. So basically the transfer function from this input referred noise voltage to the current is a short circuit GM, so that is straight away known. Is that okay? So now we will just find the noise current here due to all transistors, and then divided by this transfer function that gives the input referred noise. Okay. So let's do that. So let me erase this. So this is something we know already. This is GM1. Okay. So now we have 5 transistors, so we'll have contributions from all 5 of them. So let's first find the short circuit noise current I out, and once that is found out, the input referred noise is basically I out by GM1. Okay. Right. So let's start with the input transistor M1. So again, to model the noise for this input transistor, you can consider it to be an input referred voltage noise for the transistor. So now can you tell me what will be the contribution of this transistor M1 to the total input referred noise voltage? Okay, let's take a hold on, let's pause. See, we know that for a transistor, ideally, although the current noise should be noise should be modeled in terms of the current. If we ignore the gate cap, we can model it using a voltage source like this, right? Now let us say you take any amplifier, let us say input is fed here, and then you have the rest of the circuits. It has a bunch of transistors here and resistors inside, right? So now the idea is you want to find the input referred noise for this overall circuit, right? So what we'll do is the following: we'll short the input, right, and then find the short circuit noise current, whatever, and then our model will be this, the same network. So this is the same network without any noisy elements. I mean, without any noise in the network. That's fine. So this is our original noisy network. We are trying to model this like this using a single voltage source. Now this input referred noise voltage will have contribution from this transistor, and all the other noise sources inside, right? Now to model the noise generated by this input transistor, I can consider it to be an equivalent voltage source at the gate. So now can you tell me what will be the contribution of this transistor to this overall input referred noise? Or let me put it this way, let us say there are no noisy elements in the network, right? This is the only transistor contributing to noise, right? So technically what I'll do, I'll find the short circuit noise divided by the transfer function and then model it to be an equivalent voltage noise like this. So can you see what will that be? It is same as this, right? Is that okay? See, this is basically your input port, and the input for this transistor, the noise is modeled as an equivalent voltage source at the input, right? So the contribution of this transistor to the overall input referred noise of the circuit is basically the noise voltage of the transistor directly. Should also make sense because you are going to apply the actual input signal here. So the input is basically getting added to this noise. So that is basically your input referred noise. Is that okay? So basically for all our op amps, if you look at it, the input referred noise will have contributions from all transistors. But for the input differential pair, the contribution to the input referred noise voltage is basically the corresponding noise voltage for the transistor. So that's one straightforward result. So here now can you tell me what will be the contribution of M1 to VNN? It's basically VN1. Similarly for M2, it's VN2. Right? And this has a pass spectral density of 4 kT gamma by GM1. This will also have 4 kT gamma by GM1, assuming GM1 and GM2 are same. Okay. So this is straightforward, so you don't have to worry about this guy. Fine. So now let's look at M0. For M0, I'll model the current like this. Again, gate is incrementally short. This is incrementally short. Okay. So let me call this noise current as IN0. Now this current has two paths to flow, either here and here. So what will happen? Yeah, so what is the resistance looking here? 1 by Gm because this drain is at a low impedance. This one by Gm because this drain is also short. So the noise current is going to split equally. So this is, let us say, IN0 by 2. This is also IN0 by 2. And remember, the current in this branch is same. So M3 and M4 form a current mirror. So whatever current flows in the diode connected transistor, that gets mirrored onto M4. So now what is the current that will flow into the output? 0. Okay. So nothing flows out here. So here it is 0. So that is another thing to observe. As long as your circuit is responding to the differential signal, any noise injected at the common nodes or any common mode noise that is getting injected into your network will have no effect at the output, provided the output is dependent only on the difference between the two signals. And here we know for a fact that the output voltage depends only on the difference V1 minus V2. So any common mode noise that completely gets cancelled. So that's why this doesn't come into play. Okay, so now we are left with only 2 more. Let's do that. Let me erase these things. Yeah, so now let's look at M3. For M3, the noise current, let us say I model it like this. And I mean, this is basically the top side is ground, incremental ground, so I'll maybe redraw it differently. So I'm just saying that the current is injected like this. Okay. Right. So now you see, I mean, let's all assume R0 to be infinity for noise calculations, right? So looking down, it's completely open, right? So now you see that I am injecting a current source into a diode connected transistor, and that's copied onto transistor M4. This is your classical current mirror. So whatever current you are injecting here flows to M3, that exactly gets mirrored onto M4. So the current in this direction is same as IN3. So what is my I out? Minus IN3. So if I refer it back to the input, I will divide it by GM. So it's minus IN3. 11. Ask, it's okay.
IN3 is going directly into it will create voltage.
Yeah, I mean, the point is, yeah, that's what happens, right? See, if you look at this voltage, what will that voltage be? IN3 by GM3. That is your gate voltage. So now this is the gate voltage. What will be the incremental current? That's all. That's what happens. But if you this you can directly look at it in the form of a current mirror. So,
why wouldn't any current flow through F1?
Okay, we have ignored the R0 of M1, and even if that is there, looking up it's 1 by GM. Looking down, it's going to be some large resistance, let us say. So assuming, I mean, most of the current will flow there. So M3 is done. So let's do M4. That will finish it. M4 it's straightforward. We can model the current like this. So now what is the short circuit current due to IN4? The entire current will just flow to the short circuit, straightforward. So it's going to be IN4 by GM. So this is your total input referred noise voltage. You can write the pass spectral density and wrap up. So let me copy this. So this is my VN in. So if I write the pass spectral density, due to VN1, VN2, I'll have 8 kT gamma by GM1. What about this guy? What is the pass spectral density of this fellow? 4 kT gamma GM3 is the current pass spectral density by GM1 square. Right? For this guy also it's same. M3 and M4 are identical, so this just by 2. I am directly adding all the pass spectral densities because each of these noise sources are uncorrelated. Let me just remind you that once, so that. So if I simplify it, it's basically 8 kT gamma by GM1 times 1 plus GM3 by GM. So now let's stare at this and see if we can make any sense. So, sorry.
So in the noise for M4,
Mm-hmm.
when you're referring the voltage back to the input, where exactly are you?
Referring to the differential input, right? That's all. It's an OTA. We don't care where exactly it is there. In this differential input, whatever is the noise getting added at the input. That's all.
So this is GMO.
Yeah. So now the first term is basically the noise contributed due to the input transistor. So if you were to reduce the noise, what is the only solution? You have to increase GM1, that's all, right? Or you go to Antarctica make temperature go to 0. So practical thing is go and increase GM1. That boils down to increasing power. Okay. So that is something. And what about the second thing? Is there to reduce a noise contribution due to the current mirror, what can I do? Yeah, for that we have to reduce GM of the transistor, right? So for M1, M2, you have to increase GM. For M3, M4, we have to reduce the GM3. And also here, remember that the tail current will be fixed by some other thing. Let us say some slew rate or something fixes your tail current source. So the current here is I0 by 2. So the current in the transistor M3 is fixed. Now for a given current, if I reduce GM3, what happens? What changes? No, size is not, we are not changing size, right? Let us say, okay, so you can reduce size also, but what I am saying is GM is what? 2 times the current OTA voltage, right? So essentially, if GM reduces for a given drain current, it boils down to the fact that overdrive increases. Okay. They reduce the weight overdrive. But same thing, right? Bottom line is that. So you can do that, but if overdrive increases, what can you say about the gate voltage here? This voltage, gate voltage for the PMOS, same as the drain voltage for the NMOS, that will keep reducing. If the drain voltage reduces, what can go wrong? This can go to saturation, so there is a limit, right? So you can't keep doing this randomly. Okay. So that is with the noise of this guy. So parallelly, let's also look at the mismatch effect, right? So once again, to refresh the takeaways on mismatch. So recollect that any two elements, supposedly identical elements, will have mismatch, and it's a random phenomenon. So we typically except the threshold voltage mismatch, everything is normalized, and being a random quantity, we are interested only in mean and variance. Mean is 0, and the standard deviation of all the relative mismatch, how is it related to the area? It's inversely proportional to the square root of the area, number 1. Also, if we have two supposedly identical transistors, what are the sources of mismatch? What things can be mismatched among these two? The current factor beta, that includes your mu COX W by L, and the threshold voltage. To model the mismatch in the current factor beta, what do we do? Recollect? No. See, the idea is, these are not matched. We'll assume that the transistors are matched, but the mismatch in current factor is modeled using an additional current source. Similarly, for threshold voltage mismatch, how do we model? Yeah, we assume that the transistors have the same threshold voltage, but the error is coming due to a hypothetical voltage source added to the gates of any of the transistors. Okay, that's a deal. And what else? Yeah, so now, so which means now if you take all your differential amplifiers, which form the basis of all your op amps, so you are going to have this structure. So you'll have something here and then something here. So any two identical transistors in this circuit will have mismatch. So which means what will happen is the following. If you take your OTA, ideally if all transistors are mismatched, if I zero the input and measure the short circuit current, it will basically look like this. Right? This is your input, this is your short circuit current. It will exactly be 0 if the input is 0, but now because of the mismatches, you will have some offset here and there. Right? So once again, the offset will be due to mismatches in every pair of transistors in your differential circuit. So to model this, what we do is the following, same thing as noise. So this is your actual thing. If this has mismatch, for 0 input, the output current is not going to be 0. To model this offset, what we do is the following, we assume that the OTA is properly matched, and the offset is coming due to a hypothetical voltage source added to either positive side or negative side, just like noise. Okay. So again, to find out this input referred offset voltage, the procedure is same. You take your transistor with mismatch, zero the input, find what is the current that is arising due to the mismatch in the transistors, divide that by, what should I divide it by? Yeah, what is the transfer function here from this voltage to the current? The short circuit GM. Okay. So the input referred offset voltage is simply your short circuit current when your inputs are 0 divided by the short circuit GM. That's all. Okay. And once again, this offset will have contributions from each pair of supposedly matched transistors. But if you look at the contribution due to the threshold voltage mismatch of the input differential pair, so to model the offset due to the input pair, we can model it using a voltage source at the gates of one of them. Say if this is say M1 and M2, I'll say delta VTH12. So can you comment on what will be the contribution of these guys to offset voltage? It is going to come directly. Again, the argument is same. Assume that these are the only mismatched transistors. We are going to model the offset by an equivalent voltage source at the input. Now, to model the mismatch of these two transistors, you are using a voltage source at the input. That's going to be the same. So just like noise, the threshold voltage mismatch due to the input transistors is going to directly appear in your input referred offset expression. Okay. And usually this threshold voltage mismatch is what is dominant, so we will not consider current factor mismatch at all. Okay. Cool. So now if this is fine, let's do the calculations for finding offset here. So I'll take the same 5 transistor thing. So now erase all this. The procedure is same. You find the output short circuit current due to the mismatch in threshold voltages of this guy and this guy divided by GM. So now we have two sources, mismatch in transistors M1 and 2, mismatch in transistors M3 and 4. So already you know the transistor threshold voltage mismatch in M1, M2, it directly appears in your input referred offset. That is straightforward, don't have to worry. Now let's look at the contribution due to M3, M4. So once again, first let's try to find the short circuit current. So to model the mismatch in threshold, we'll again assume that the transistors are matched, but I have a hypothetical voltage source here, right? So again, these are all small signals because the mismatch is going to be small. So if delta VTH is 0, what is the small signal current? 0. Delta VTH is 0, this is 0. So now, okay, if delta VTH is 0, this is also incrementally ground, remember, right? No changes in any of the voltages. If there is no change incrementally, this is also 0. Now what you are saying is, if this was incrementally 0 earlier, now this gate voltage is at a potential delta VTH34. So what is the small signal current it will draw? Okay, can you be careful with the signs? It doesn't matter, but minus GM3, let's say GM3 is fine, delta VTH3. The signs don't matter for offset, but it's always good to be consistent with this. So this is the short circuit current. So to find the input referred voltage, I'll divide this current by the short circuit GM, which is GM. Right? Sorry.
So mismatch can happen between any two transistors.
Correct.
Right? So for characterizing mismatch, what we do, we fix one transistor. Supposedly the size what we want, it is the size what we get.
Okay.
And we add some voltage and like current source to the other transistor.
I don't know.
I'm saying like, suppose there is a mismatch between two transistors. I assume that the first transistor is perfect.
Okay.
And the second transistor adds some voltage source and current source to characterize that mismatch.
Yeah.
So going by that, there should be mismatch between 1 and 3.
No, but the thing is, if these two need not be matched in the first place, right? The idea is, mismatch is we are talking about mismatch between two supposedly identical devices. Right? In all your calculations, we assume GM1 is GM2 and GM3 is GM4. Right? So we are looking into what will happen if that assumption is not valid. So, right? Because I mean, what you are saying is that the properties of this transistor can change compared to what you thought, what we decided. That is basically the process variation, right? Now mismatch is basically between two identical devices. Here also the property of this guy will change from this guy, but that violates your assumption that GMs of these two transistors were equal. Okay.
Process variation is different from mismatch.
See, process typically is from chip to chip, right? Mismatch is within chip. Okay. So here what you are saying is the transistor M3, you thought it has some value, now it has some other value. That is okay. What that means is GM of this guy is different from what you had. That is not resulting in an offset, isn't it? Offset happens if you for 0 inputs, if you should be getting 0 output. If that doesn't happen, there is an offset, right? And that offset will happen only if there is a mismatch between two supposedly identical devices. Right? I mean, let us say there is no mismatch between these two, but let us say again there is no mismatch between M1, M2, M3, M4. They are perfectly matched. But let us say compared to what you thought, GM of M1 and M2 have changed. That is okay. There is no offset, which means GM has changed. Some things will change in your small signal calculations, but offset is not there. That's all. And that is why, I mean, the variations in GM and all that you have to take care in process simulation, because as you know, the transistor properties will vary. So before you sign off your design, you have to make sure your specifications are met at all possible process corners typically. So most of the time you end up over designing. You design for the worst case so that at the worst case it is met. So it is always usually over designed. Okay, so now we have got this. Let us write the expression for this. Input effort offset is delta VTH12 minus GM3 by GM1 delta VTH34. So again, I'm only interested in the standard deviation and variance. So if I take the mean squared of this, what you will have? Mean squares will add because they are again independent. Yeah, so this will be 1 square. And once again, you know, sigma delta VTH is, you can write it like this, some A VTH by square root of WL, right? So you can work it out. So which means now again we can make some observations. So to reduce the mismatch due to the input pair, what is the only option? You have to increase area. That's the only option. For reducing the mismatch due to M3, M4, of course you can increase the area, that will reduce this quantity directly. But what is something else you can do? Yeah, increase GM1 or reduce GM3. Right? So if you reduce GM3 for a given current, as you know, the overdrive voltage increases. And that should also make sense, because if you had a smaller overdrive, say 100 millivolts, a 50 millivolt change in your threshold voltage results in a lot of variation in your effective overdrive. But if your overdrive was larger, say 500 millivolts, 50 millivolt change in threshold is nothing. Okay, so
this offset voltage we will actually apply to match them after design.
Oh, you to correct for the offset? Okay, there are different ways in which you can tackle offset actually. Yeah, one is basically somehow, yeah, one is what you suggested. So let us say this is your amplifier. The offset is modeled like this. Okay, this is your final amplifier. This has an input referred offset like this, right? So to correct for it, if you can somehow add another voltage source with the opposite polarity, then effectively there is no offset. So, but yeah, now the point is, how do you exactly find what this is and stuff? This is one way in which you can do. This is called auto zeroing actually. So you somehow estimate your offset in the amplifier and store that offset in a capacitor. I mean, you can't have a voltage source, right? The closest to voltage source is a capacitor. You have a capacitor charged to that particular offset voltage, put it in the appropriate polarity so that it cancels. That is one way in which it is done.
Isn't the offset random?
It is random. For each chip you have to do, right?
You can like determine that voltage source.
No, it is random, but it won't change. It's a DC. See, random meaning from one chip to other chip there is going to be different offset. But in a given chip, the transistors are fabricated.
Like every time I run, it would be the same.
Yeah. There can be variations for temperature, but as long as temperature doesn't change so much, you're okay.
So is this an external thing here?
Yeah. See, this is basically, I mean, actually the op amp is this, right? This has an offset. The offset I have modeled it like this now, right? So these are your inputs, outputs. This is your term. Let us say pin 1, pin 2, pin 3 of your op amp. Now, if you directly feed in the input, there is an offset. So you add an extra capacitor here charged to the appropriate offset voltage in the correct polarity so that it cancels. This is one way. There are a bunch of ways in which you can tackle offset actually.
So in some op amp, I see there's a separate pin for offset.
Yeah, that is there. So basically there what they will do is you have some programmable current source and they inject currents and appropriate nodes to cancel the mismatch, right? I mean, it depends on, that's what, there are different ways in which you can do. Cool. So now this is done. Let's quickly do one more. So after this 5-transistor OTA, what did we look next? Yeah, cascode. Let's do the telescopic cascode quickly and finish today. Okay, that's okay. Okay. So let me do telescopic cascode. I'll have to draw this. Okay. That's okay. I'll draw this quickly. Right, so let us say M1, M2, let us say M3, M4, M5, M6, M7, and these are connected to some bias voltages appropriately. So let's start with noise quickly. So again, the short circuit GM is GM of this transistor. The transfer function from the input differential voltage to the output current is GM1. That doesn't change. So let me put all the transistors. So M0, M1. Okay, let's do. Now we should be able to do it quickly. So what is the input referred noise contribution due to these two guys? The same Vn1, Vn2 that I can directly write. Fine. Let's look at M0. What do you think will happen to the noise due to M0? It's the same thing. This will equally get divided in the two branches. So here I'll have half the current. Here I'll have half the current. So nothing glows. So that is 0. So now let's look at these guys, M7, M8, which are these cascode devices. Again, we'll assume that R0 of all the transistors are ignored. So let us say I model the noise current like this. Let us say I start with M8. What can you say about the short circuit output current? 0. Again, it's cascode device. I am assuming R0 is infinity. So looking down, it is open circuit. So basically it is open like this. So since there is no path for the current, nothing will flow at the output. Okay. I mean, you can also look at it like this, right? So let us say I can model the noise here due to, like a current or a voltage, right? So let us say I use a voltage source. Incrementally, these are all short, remember. So I can model the noise due to M8 as a voltage source like this, right? Now, if looking down its infinite resistance, what can you say about this voltage? It's basically source follower. I'm applying the input at the gate, tapping it from the source. Looking down, I've told R0 is infinity. So the same voltage comes. VGS is 0, current is 0. So basically for M8, no contribution. What can you say about M7? Yeah, M7 is also a cascode. So if you try to do the same exercise, let us say you do this Vn7. Again, looking down, R0 of M1 is also infinity. So no current will flow. So this will also be at Vn7. This is the nice property of cascode. So he'll silently come and help you. No noise. So similarly, can you say about M5, M6? What are the, what is the role of the transistors M5, M6 here? It is cascoding the PMOS stage, right? So what can you say about the noise due to them? They'll also be 0, same way. Again, if you try to do the same thing, R0 of M4 is infinity. So if you model the current like this, R0s are all infinity. So M4 is open. There is no incremental path. No path for the incremental current to flow. Current will be 0. So similarly for M5 also, it will be the same. So I will not spend time on that. So all M5, M6, it's all 0. So pending things are M3, M4. Let's look at that. So let's do for M3. M3 again the current. Okay, let me just clear these things. This is M3. So now let us say this is the current IN3. Now you see that this current is injected here. This guy is a current buffer. It will basically buffer the same current, and the same current will flow into the diode connected transistor M3, right? So which means the same current will be mirrored here. So what is I out? Minus IN3. Is okay. So the only difference compared to the earlier 5-transistor OTA is now the noise current is injected into the input of this current buffer. So this current buffer will basically take in the current, and that will basically flow, generate the appropriate voltage. It will be again IN3 by GN3 blah blah blah, and then it will get. So this is basically minus IN3. So it's minus IN3 by GM1. Similarly, what can you say about M4? M4 should be easier. If I do it like this, what happens? Now the current is injected at this node. You can, in principle, it can flow here or here. Where will it prefer to flow? Looking down, because again R0 is infinity, so up this side it's completely open. All the current will flow down and this come here. So now we can clearly see it. Sorry? Yeah, but still that will be small, right? If that was not there, it will be basically, you'll have 1 by 1 plus gm R0 kind of behavior. Okay. You'll have 1 by gm plus R0 plus 1 by gm kind of thing. Okay. I don't have it. Luckily. So what I'm saying is, see, you can, it's not very straightforward, but I just give you a qualitative explanation. So this current is injected at this node. This is the input of a current buffer, which is this cascode device. So this current buffer will basically buffer this current and make sure that it flows into the diode connected node of M3. Now it is like a current mirror formed between M3 and M4. Okay. So actually give this as an exercise. You can actually find out what will be this voltage. Right? It will be interesting to see. Again, ignore all R0s and try to find what is Vx. Anyways, so now you can clearly see the input referred noise is same as what you got for your 5-transistor OTA, right? So if you're not convinced, I can show here. This is what we had for the 5-transistor OTA. The input transistors added directly, and for the current mirrors, it was IM3 and IM4 by GM. Same thing you have, no difference. So let's also quickly do the offset and wrap up. So now we are interested in offset. Yeah, let me just erase this. So once again, we'll have offset now from what all transistors? Which all transistors can result in offset? Yeah, you'll have M12, all 3, 4, 5, 6, 7, 8, that's all. Again, we'll consider only threshold voltage mismatches. So what will be the contribution to the input referred offset voltage from the input pairs? From the input pairs, what will be? It will just be the delta VTH12. Right? Let's look at the cascodes now. Let's look at M7, M8. Okay. So again, the mismatch in the thresholds in these two transistors, we model it like a voltage source added to the gate like this. Right? Now once again, what can you say about the short circuit current now? 0. As long as R0 is infinity, nothing flows to the output, same as what we had for the noise, right? So M7, M8 contributes to 0 offset. Similarly, what can you say about M5, M6? That will also be 0. Only thing pending is M3, M4 that we can go to next page maybe. You model the mismatch like this, delta VTH34. So once again, the way you look at it is, if delta VTH is 0, no current flows. This would have been at incremental 0. Now on top of this, this gate is at a voltage delta VTH34. So the incremental current here will be minus GM3, GM4 delta VTH34. So this will be minus GM3 delta VTH34. So the output will be GM3 by GM1. So once again you can write the mean squared value. That will be same as what we computed for the 5 transistor case. And yeah, that's all. So let me write it and finish it. The input referred offset is the threshold voltage of M1, M2 that will appear directly, and the mismatch due to the current mirror is scaled by a factor GM3 by GM1. Okay, so if I write the standard deviation, sorry, mean squared or the variance, so it's this. Okay. Cool. So yeah, so now you can see, I mean, this noise offset calculation, and there is nothing very different and big there. As long as you are comfortable with small signal impedance and transfer functions, that's what in the initial part of the course you were practiced to do. This should be straightforward. All you need to know is noise due to a transistor is modeled either as a current source here or as an voltage source here. Now depending on the situation, use whichever is convenient, right? For with respect to the input transistors, modeling it like a voltage source was convenient because they directly gave you the input referred voltage. For other guys, it is nice to model it like a current and do. And offset also same thing. Assume that a hypothetical voltage source is added between the gates and then find it. So that's why if you are comfortable with these impedance calculations, which I hope by this time you should be okay with, this should be a cakewalk. So I'll stop here.